Hello everyone, you're welcome to this channel once again. Today we shall be discussing on airflow through a converging diverging nozzle. Once again, airflow through a converging and diverging nozzle. Now let's read to the question we're given today. And here enters a converging diverging nozzle shown above at 1.0 megapascal, which is 1000 kilopascal, and 800 Kelvin with negligible velocity. The airflow is steady, one-dimensional, and isentropic with K factor of 1.4 for an exit mark of 2. And the throat of 20 centimeters squared. Now, calculate the throat conditions, that is all the stagnant condition, and the critical condition at the throat. Don't let us forget that at the throat of a nozzle, the Mach number is always 1. So therefore, by pulling out all the parameters given in this example, first of all, by pulling out, we're given the isentropic K constant, which is 1.4. We're given the stagnant pressure, 1.0 megapascal, which equals 1000 kilopascal. We're given the R gas constant, knowing fully well that our here is agreeing with ID gas law. So our R constant 0.287 kilopascal per meter cube per Kelvin. Also, we're given the temperature at the stagnant, which is 800 Kelvin. Now, by using the ideal equation, which is rho O, that is the density at the stagnant point, equals the pressure at the stagnant over the R gas constant multiplied by the T temperature at the stagnant. So therefore, our sigma, which is the density at the stagnant, rho O equals 1000 over 0.287 times 800. So therefore, our calculated density at the stagnant equals 4.36 kilogram per meter cube. Now, by going through table A32 of appendix of property table and chart, once again going through table A32 of property table and chart, looking at the compressive flow for one-dimensional function for an ideal gas. Once again, checking the dimensional isentropic compressive table on table A32, we can find that at the throat condition, the Mach number is always 1. So therefore, the ratio of the critical pressure to the stagnant pressure equals 0.52. Also, the ratio of critical temperature to the stagnant temperature equals 0.833, and the ratio of the density at critical to the stagnant equals 0.639. So therefore, by plugging our value for all the stagnant value here, we have our critical temperature to be 52.8.3 kilopascal, and also our critical temperature to be 666.6 kilopascal, and the density on the critical to be 2.76 kilogram per meter cube. Also, by using the critical velocity equation, which equals Vc equals the root of Kr over Tc, give us the root of 1.4 multiplied by 0.287 multiplied by 66.6, which gives us 517.5 meter per second. Now, we have calculated all the throat condition, that is the critical pressure, which gives us 52.8.3, and the critical temperature at the throat, which gives us 666.6 Kelvin, and the density, which gives us 2.76 kilogram per meter cube, and the critical velocity, which gives us 517.5 meter per second. Thank you very much for staying tuned.